Section 11.1, this is part A, the covalent bond. And these are the things that we're going to talk about in this video. Be able to explain what covalent bonds are and why covalent bonds are formed, and then compare them with ionic bonds in terms of definitions and how they're formed and so on. Alright, if you recall, in ionic bonds, when we had those, we usually had a metal and a nonmetal, and the metal gave the electron to the nonmetal, produced the cations and anions. There was that electrostatic attraction between the two. That's an ionic bond. In covalent bonds happen with two non-metallic atoms. And because one is not stronger than the other to take that electron, or at least not strong enough, they share. So these electrons share. And in other words, what happens is those orbitals, the areas where the electrons circle the nucleus, they overlap, and so these electrons are shared between those two atoms. Take a look at this video that talks about how ionic versus covalent bonds.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has one valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level.
So notice how they're going around both.
A hydrogen atom with one valence electron needs one additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still one short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
So in that animation you saw that in the covalent ones, the electrons go around both of the atoms, not just one, like that happens in the ionic bonds. Alright, you can also, when you're forming these, you can form single, double, or triple covalent bonds. And single bonds would be where we're simply sharing two atoms are sharing a pair of electrons. So, we've got the hydrogen, these electrons are being shared. There's one pair being shared between. In a double covalent bond, they're going to share 2 pairs. A triple covalent bond will share 3 pairs. And here's a little short animation kind of show you some of how that works. So take a look at this.
One or more atoms may share electrons, thus forming a covalent bond. Electrons will spend a portion of their time associated with each of the participating atoms. A single covalent bond represents the sharing of one pair of electrons, such as with 2 hydrogen atoms. A double covalent bond is formed by the sharing of 2 pairs of electrons. Atoms sharing 3 pairs of electrons form triple covalent bonds between them.
Okay. When they form these bonds, there's 2 different kinds of bonds that are formed when they form things. There's things known as sigma bonds. Sigma is a Greek letter, looks kind of like an O with a little tail on it, kind of like that. Sigma bonds, think about this. If this is my nucleus, between two atoms, and let's say we draw a line between those, sigma bonds would be over that line. They would be, parallel with that line. They would be back and forth. Pi bonds, think of the p sublevels, and we've got those dumbbell-shaped kind of things. And here's my nuclei, and the bonds are formed up here and here, and so here's my line that goes through the nuclei, and notice that they're not going in that same here. They're above and below that line. I know that's kind of a bad explanation, so take a look at this video that kind of demonstrates and shows you what they look like here. So take a look at this.
Describe sigma and pi bonds. Well, if we imagine two hydrogen atoms, you can see their s orbitals there.
So remember, s
When they
orbitals are
react
round,
to
spherical,
form the molecule H2,
and then when they form
they
it, they form
make a
this,
single covalent bond,
and
which is called a
that
sigma
bond is
all single bonds are
right
sigma
along
bonds.
that line. Okay.
And all sigma bonds go along the internuclear axis. If you imagine a line that joins both nuclei, that's the direction the sigma bond will take. And if you have two fluorine atoms, when their p orbitals overlap, just like this, that also forms a sigma bond, which is a
So on both of those, the bond is at the same, what they were talking about between the two nuclei. That bond goes over the line between those. It covers that line, basically. Okay, those are sigma bonds.
single covalent bond. Now for hydrogen fluoride, HF, the s and the p orbitals for the H and the F respectively again form a sigma bond, single covalent bond, that goes along the internuclear axis. The final sigma bond creation you need to know is, for example, in methane, which is between hybrid orbitals and, in this case, hydrogen. Now that looks quite complicated, and there'll be more detail about that in further videos. So that's the sigma bonds dealt with. If you have two atoms with parallel p orbitals, and those p orbitals are brought close enough together to overlap, you're going to form a pi bond. So the top and the bottom lobes kind of mold into those blobs. Now those small donut shapes are where the nuclei would be. So it's parallel to the internuclear axis. The p orbitals initially were parallel to that internuclear axis, and that gives you a pi bond. Now if you had a sigma bond and a pi bond, you've just made a double bond. Now it looks like there's three bonds, but it really isn't. It's just a double bond. And for a triple bond, well, you're going to get in another pi bond at 90 degrees to the first one. So that's now a triple bond.
So what they're talking about here is the shape of these orbitals that overlap. So remember, we talked about s orbitals were spherical, p ones were dumbbell shaped. When they form these bonds, the orbitals change shape, and this is what they look like. And you need to understand a little bit about sigma bonds and pi bonds. Okay, if some things can have both covalent and ionic bonds, we've talked about this a little bit, but the polyatomic ions, they're covalently bonded, but they react like an ion. And they form ionic compounds with another ion. So the main part of it, I mean the covalent ion, the polyatomic ion, the ones that we talk about, those like NO3 and OH minus and so on, those are bonded covalently, and then they work like an ion and bond to another metal. Bond strength, usually when they talk about that, they're talking about how much energy it takes to break a covalent bond. And the more energy it takes to break this bond, the bond strength is considered to be higher. So if it takes a lot of energy to get that bond apart, it would have high bond strength. Usually when they measure bond strength, they do it in what's known as kilojoules per mole. Now, we really haven't talked about moles yet, but mole is simply a number. It's a really big number. It's 6.02 times 10 to the 23rd. So if I had that many atoms, or molecules, let's say, of HBr, it would take 365 kilojoules to break those bonds in there. And as far as stability, the more stable compounds, they usually give off energy because the bonds that are formed have lower energy. In other words, if the bond takes less energy to be formed or to be maintained, then that's a fairly stable thing. So molecules are always trying to get to more stable configurations. If they can change their configurations down to more stable things, they'll do that. So for instance, when you take glucose, C6H12O6, that has a very high energy, lots of energy here. And we can lower that energy, and basically by adding oxygen. This is a process called respiration. When you breathe in oxygen, your body takes glucose, adds that oxygen, and produces carbon dioxide, which you breathe out, and water. And the bonds here have much less energy. So what you get from that, you get a lot of energy, and that's what we use as animals. Animals get that energy and use it for things that they need to do. And so we get it from the bonds in here. All of those bonds are broken, made into smaller molecules, less energy, and we use that energy. And that's the first part of section 11.1.